Welcome. In this video I'm going to show you how you can perform a Pearson chi-square test of independence using Python and JupyterLab. Now this is a different test than the goodness of fit, and this is a test that's usually used if you have two nominal variables and you want to know if one might have an influence on the other. So there is a problem though, that the minimum expected count should be at least 1, and there shouldn't be too many cells with an expected count less than 5. So we'll have to check in on that as well. To show you how this test works, I'll be using an example, and for that example I'll need to import some data, which I'll import as a pandas data frame. So I'll first need to import pandas, and you can install pandas by running this line if you've never used it before. I'm going to import pandas and call it PD, so I won't have to type pandas every time. Now to look a quick look at the data, I can use pandas PD now, read CSV function, and then using the head to show the first 5 records. So there's quite some data in here that actually gives me a warning, but that's irrelevant for this example. I'll be using the marital status and the marital ones. Mar1 is the marital status, and sex, gender, as the two nominal fields for this example. So I can select those, and then to get a quick look from the counts of both of these, I can use pandas cross tab and simply enter those two fields. And when I show then my cross table, I get a nice cross table showing that, for example, 50 people were female and separated. Now to perform the test, I like to make use of chi2 contingency, which is from the stats module, and then which is in the SciPy library. So we also have to install, if you've never done that, SciPy, and then from SciPy stats import that chi2 contingency. So let's load that in, and then I can simply feed that cross table, and I'm going to actually store all the results separately. So I have the chi value, the p value, degrees of freedom, and expected values, so that I get all of those as a result, as you can see here. Now this is not a lecture about how to interpret all these results, but quickly, the 16.999 is the chi-square value. So this is then the p-value, which tells me that there's almost a 0.002 chance of having such a chi-square value, or even more extreme if the assumption about the population is true, the assumption being that there's no association between the two variables. So usually if it's below 0.05, then that's considered low. So we would state in this case that there is a significant association between those two variables. Now the third one, the 4, is the degrees of freedom, which is usually an indication of the size of the table, the cross table, and it's simply the number of rows minus 1 and the number of columns minus 1. And these are the expected values. These are the values, the counts that we would expect if there would be no association. And to some extent the chi-square test then checks if these values differ a lot from the values that we actually have. Now, like I mentioned earlier, there should not be any in here in those expected counts that is less than 1, and many have a threshold of about 20% can have a count of less than 5. Now, as we can see here, there are none, but if you want to actually calculate that, you can simply find the minimum value by using the min function, which in this case is 35 of those expected values, and that's why up here, sorry for the scrolling, I store them separately. And to see the percentage of cells that have an expected count less than 5, what you can do is you can get the expected array and then only select those where that's less than 5, and then divide it by the number of counts that you actually have in the expected values, and then multiply all of that with 100, so that you know, so that you can see it as a percentage. And that should be then less than 20. In my case it's 0 because there were none. So instead of the SciPy package, there's a slightly lesser known package, which is ResearchPy. You can also use that. So import it first, And you then get the cross table, the results, and the expected values. And just to show the results, it nicely shows it as a pandas data frame, and the expected values are similar as a pandas data frame, so same results as before. If you're really interested in the appendix, I'll actually go over the entire formula if you want to avoid using libraries as much as possible. The whole chi-square value, there's its big formula. I'll put this Jupyter notebook in the description below as a link, so you can then actually install it. I do use a package there for the chi-square distribution in the end, but it's just more like a theoretical exercise. Alright, I hope this was helpful, and if you have any thoughts or suggestions, please let me know in the comments below. Thank you for watching.